Good afternoon, everyone, and welcome to what I think is your final session of the day. I'm delighted that you've chosen to use the National Space Centre for your conference today. My name's Ojha, and I've got a number of roles. I'm one of the directors here at the National Space Centre and also an academic at the University of Leicester. I'm a senior advisor to the European Space Agency's Division of Human Spaceflight and Exploration, and I've also got a role within the United Kingdom's particle physics and astronomy research structure. But what I want to talk to you about in the remaining 45 minutes is the answer to this deliberately provocative question. Space, so what? What difference has space science made to our everyday lives? What are the drivers for exploration? And what have we got coming up right now on the horizon when we're looking at our ambitions in space and what we're hoping to achieve? I hope you're going to enjoy it. It goes on for about 40 minutes, and if I have time at the end, we'll have about 5 minutes for questions and answers. But the first thing I want to start with to set the context is the idea of how far away space is. Because when I pose this question to the general public, the numbers that come to mind are sort of millions of kilometers or light years or thousands of miles. And the answer is surprising because the internationally accepted boundary of space is only 100 kilometers away. It's closer to where we are now than the centre of London, and certainly closer than the distance many of you have travelled in getting here from across the United Kingdom or across Europe. The problem is, of course, that 100 kilometres is straight up, and if we want to get up there, we've got to battle, in terms of gravity, against a force that's dominated the way that life evolved on this planet for billions of years. If we want to stay in the space environment, we are dealing with an environment from a radiation, from a thermal, from a pressure point of view that's far more challenging than anything we find naturally here on the surface of the Earth. So even though we've been doing space exploration for more than 60 years, it's still pushing our engineering and our technology to its very limits. But when we finally get beyond that, quotation, final frontier, the view is absolutely breathtaking. This is time-lapse photography taken from the International Space Station, and it's the sort of imagery that astronauts on board the ISS enjoy during their 6-month periods on board. And what I love about it is not only do we get this incredible view of the cosmos, unfettered by the atmosphere, but we also get a living geography lesson when we look down and we see the pattern of city lights and the patterns of human development as they evolve over relatively short time scales. Now, one of the biggest challenges of getting into space is literally that. How do we get up there? Because what we tend to forget when we see images taken from space platforms like the ISS is that we're not serenely drifting around the Earth. We're in an orbit falling, in the case of the ISS, at a velocity of 5 miles or 8 kilometers every second. That's here to London in 20 seconds. And in order to get there, we've got to get incredibly high amounts of kinetic energy. And the only way to do this is by harnessing massive, high-yield exothermic chemical reactions. In short, a controlled chemical explosion that we're trying to channel in the right way to use the laws of physics to get into space. Now, what you see on the screen at the moment are 3 traditional launch vehicles or rockets. On the left, we've got the European Space Agency's Ariane 5. In the middle, we've got a Chinese Long March. And on the right-hand side, we've got a Russian Soyuz launcher. Now, they look different. They've got slightly different designs, but they're all working on that same fundamental principle of exothermic chemical reactions. And the other thing that they have in common, and it's the same for all rockets, is that when it's sitting on the launch pad, more than 85% of its mass is propellant. It's fuel that is thrown out of the exhaust in the first few minutes, and only 15% or less is that final payload that you get into orbit around the Earth or going out into the solar system. That's one of the reasons why rocketry and access to space is so expensive. But the other reason, of course, is scale. Because on the previous images I showed, you get no idea of scale. But if I show you now an image of me back in the days when I was less follically challenged than I am now, this is me against the engines of the largest launch vehicle ever used successfully in spaceflight. It's the American Saturn V. This particular one that was unused, its mission was cancelled, is at Johnson Space Center in Texas, and each of these F1 engines was using 3 tons of liquid hydrogen and kerosene every second. So you can understand the challenges of engineering just looking at these images here. But to understand the drivers for space exploration, we need to remember our history. Because, of course, after the wreckage and carnage of World War II, what emerged from the geopolitical ashes was a competition between two competing ideologies, communism and capitalism, the Soviet Union, as it was, against the United States. And what better arena in which to showcase your political superiority to the rest of the world than the challenge to reach that final frontier? And it's fair to say that in the space of 4 very short years, the United States, which had prided itself on its technological and political superiority, took 2 body blows to its pride. On the left, we've got October the 4th, 1957, the launch of the world's first satellite, Sputnik 1, followed less than 4 years later by the launch of the first human into space, Yuri Gagarin, on April the 12th, 1961, just about completed 1 orbit of the Earth and landed a worldwide celebrity. And it was these 2 double body blows to the US pride that led President Kennedy to set what is arguably the most audacious national goal that the United States has embarked upon within the space of 10 years. Because, of course, his challenge was to get Americans to, on, and back from the moon safely within 9 years. Now, don't believe the hype that you might read about with, Kennedy thought it was technologically impossible and we had to push science and engineering to new limits. We knew it was technically possible. But of course, it would take a concerted national effort. And at the peak of Project Apollo, this target to get human beings 1,000 times further than they'd ever been, because whenever you see pictures of the Earth and the moon next door to each other, that's not to scale. The moon is 1,000 times further than the International Space Station. It would require a national goal that at the peak of its funding, in 1965, 1966, was taking 5% of the United States federal budget and 400,000 US scientists and researchers. By 1965 and 1966, it was clear the United States had raced ahead of the Soviet Union, and this culminated, of course, in these 4 magical years between 1968 and 1972, where on 9 missions, 24 human beings went to the moon, and 12 of them landed on its surface. They remain to date the only members of the human race to have explored an alien world, because that's what the moon is on our cosmic doorstep. Their footprints, which you can see here on an image taken nearly 4 decades later by NASA's Lunar Reconnaissance Orbiter, will maintain their integrity for millions of years. Because, of course, with no atmosphere on the moon, there's no weathering. We have truly left our mark on the cosmos. But the last successful lunar landing, Apollo 17 in December 1972, that was the end of the era of deep space human exploration. And many people ask why. It was a change in priorities. From the United States' point of view, the challenge, having won the race to the moon, was to try to make access to space cheaper. So, of course, they looked at developing the US space shuttle, which was a space cargo truck, and parts of it were reusable. From the Soviet Union's perspective, having lost the race to the moon, as often happened within the Soviet Union, it was almost airbrushed out of their history. They pretended for a long time that they'd never been engaged in it, and instead they changed their focus to space stations. Because the longest missions going to the moon were away for a period of 12 days. But what about a human being surviving for 1 month, for 3 months, for 6 months, for a year in the space environment? The Soviets, and then the Russians, became masters of long-duration spaceflight. And I show you this image because this is one of my favorites. It's an image of the Soviet-era Mir space station, the first components of which were launched in 1986, docking with the American space shuttle Atlantis in 1997. Now, the reason I like this picture is because in 1987, a year after Mir was launched, the Cold War was still deeply, deeply on, and I was starting as an undergraduate at university. And if you'd have told me in 1987 that I would see an American space shuttle docking with a Soviet-era space station, I would have said that's impossible. There's no way that's going to happen. But of course, in a time of geopolitical change, there are new opportunities. We began to see in the Shuttle Mir program, collaboration between Russia and the United States, and it's that led to the International Space Station. Just out of interest, could you have a show of hands? How many of you ever seen, either just before dawn or just after sunset, what we call an ISS pass, when you see this very bright object moving across the sky? Okay, it's a number of you. The reason that it happens is best encapsulated by this picture, because what you're seeing here are the photovoltaic arrays of the ISS, the solar cells that are generating electricity. It's dark on the ground, but there's still sunlight catching those PV arrays. And that's why during one of these passes, it's incredibly bright. In fact, if you've seen one, it gets almost as bright as the planet Venus at its brightest, and then suddenly it might disappear as it goes into Earth's shadow. So that's why you get these wonderful ISS passes. Now, this is a huge structure. It's the size of a football stadium. From end to end here, we are talking about 120 meters. We've got a mass of nearly 500 tons, and this wasn't assembled in one mission. This was assembled over nearly 30 missions. Excuse me for a second while I just check. My animation should have started here. Let's try again. This was assembled over nearly 30 missions from 15 countries around the world, and in many occasions, the first time these components ever met wasn't on Earth, but it was while they were orbiting in space. As an engineering project, it's probably the most ambitious project we've ever undertaken in human spaceflight. And in this animation produced by our team here at NSC Creative, we're trying to give a flavour of some of the activities that astronauts undertake, which I'll talk about in more detail a little bit later. This is also one of my favourite images from the ISS program, or from human spaceflight, because it shows how much spaceflight has changed over the last 4 decades. Because, you know, if you took a picture of astronauts or cosmonauts, so Russian space explorers, from the 1960s or 1970s, with one exception, Valentina Tereshkova, they would all have been male. They all would have been from either the Soviet Union or the United States. They all would have had piloting backgrounds, or if they were scientists, they would have been then trained up as jet pilots, and they all would have been, as I say, of European ancestry. What we're now seeing is representation of space agencies around the world, people of all ethnicities, people of all science backgrounds. So we've still got your traditional engineers like Stephanie Wilson, you've got your traditional test pilots as well, but you've also got people like Dottie Metcalf-Lindenberger, a NASA astronaut who, before selection in 2004, was a high school science teacher. So what we're starting to see now is a broadening of that human spaceflight experience. And of course, in the United Kingdom, we had Tim Peake's flight on the International Space Station at the end of 2015, going into 2016. Now, Tim wasn't the first Briton to go into space. That honour went to Helen Sharman in 1991. But Tim was the first British astronaut selected by the European Space Agency. And what I want to do now is explain what astronauts actually do and what their priorities are. You know, I think many of us have been absolutely hypnotized by some of the social media feeds and images we get from astronauts in space, but that's not what they're there for. They have 3 roles in priority. The first one is illustrated on the left by ESA's astronaut, Italian fighter pilot Samantha Cristoforetti. That is, keep yourself healthy. Because the human body, it tends to be lazy. If you're not using it, you're going to lose it. And in a microgravity environment where you're not subject to the dynamic bone pressure and stresses that you get from walking around, and you're not utilizing your muscles in the way that you would do in a gravity field on Earth, your muscles tend to atrophy. And so astronauts will spend between 60 minutes and 90 minutes every day on what we call countermeasure exercises. Here she's running on a treadmill held down by bungee cords. There are also isometric exercises and other exercises they're doing with various bits of kit to try to mitigate against this muscle loss and this bone weakening. So having kept yourself healthy, the next thing you need to do is to keep the space station healthy. The ISS, the oldest components, were launched in November 1998. This is an old structure, and if things go wrong, you have to fix it yourself. And what I'm going to show you now is 4 hours of one of the most critical roles for an astronaut in space. It's probably the least glamorous side, and if you don't do this and something goes wrong, you may have to evacuate the space station. So 4 hours condensed into about 15 seconds. And I'm hoping that video is going to go. This is repairing the space toilets. There are 2 of them on board the ISS. They work on airflow principles, and the reason why this is so important is that if you've got E. coli-rich fecal material floating around the cabin, even in small quantities, in a sealed can environment, that is a major health risk. If both toilets pack up on the ISS, we have to evacuate the station within 24 hours. Luckily, that has never happened, but we have come close on occasions. And it's only when you've done these 2 fundamental roles of keeping yourself healthy and keeping the space station healthy that you get on with your main job. And your main job as an astronaut is conducting scientific and engineering experiments on behalf of a global research community. During Tim's 6-month increment on the space station, he conducted nearly 200 experiments. And I just want to explain the story of how you get your experiment onto the ISS. Because back in 2014, a year before Tim flew, we were honoured enough by the European Space Agency and by ESA to be assigned one of 3 education experiment payloads to be sent to the ISS. And we were told, you've got 1.2 kilograms of payload space, you have got full responsibility for building it, for training the astronaut, for operating it with him in space, in this case with Tim Peake, and with doing all your data analysis on the ground. And it was a tremendous opportunity for us, but it was a tremendous challenge, because you don't just build an experiment, put it into a space rocket, and launch it up to the ISS. What you have to prove before you fly is that you can pass a battery of tests that are going to show that your material is not going to give off toxic substances, is not going to be flammable, is not going to shake itself to pieces during the rocket launch, and you have got 12 months of testing that is identical whether you've got this 1.2 kilograms of simple teaching equipment that we constructed, or whether or not you're building a 500 kilogram experiment to be on the space station in materials science for many, many years. And so just a few scenes from the testing we're doing. On the right-hand side, all of the equipment going to the ISS gets put into a CTB, a crew transfer bag. You can see in the space industry we're using a rich language of acronyms. And what we're doing here is we're putting it on a shaker table. We're trying to replicate the vibrational and acoustic environment of the launch vehicle that we're going to be using, the rocket that we're going to be using to launch our payload into space. We had a battery of these tests that we had to pass, and it's only when we did those, after a period of 12 months, that we got this. We had our flight safety certificate. This is our boarding pass for our payload to be launched into space. And the plan was to launch, not with Tim, but 6 months before, on an uncrewed space flight, which was effectively a cargo ship, CRS-7, SpaceX Falcon 9 rocket, and this was scheduled for launch on June the 29th, 2015. Now, me and my team, we'd never fully qualified a payload for spaceflight. We were beside ourselves with excitement. And I just want to show you what happened. It wasn't just our payload going up, of course. We had 4 tons of other cargo equipment that was heading up to the ISS. And so this is footage of the launch. And for the first 2 minutes, everything seemed to be going fine. And then I can remember seeing this flutter and thinking, no. Because we had a catastrophic failure of the second stage. We call it an anomaly in space flight. It's probably the biggest understatement of all time. And of course, instead of going up to the ISS, our payload and 4 tons of cargo and various capsule fragments rained down into the Atlantic Ocean. A catastrophic failure, but of course for us, you know, we're thinking, are we going to get another opportunity? Now, in spaceflight, we've always got a plan B. We don't just build one set of flight-qualified hardware, we build several. And we managed to hitch a ride within 3 months on another cargo vehicle going up to the ISS. Our cargo arrived safely. Tim was launched in December, and in January, of 2015, he undertook our experiments. And what we did is we wanted to make a suite of about 50 physics education demonstrations, but we wanted to do it in a way that hadn't been done before. We wanted this to be able to be used by primary school students, secondary school students, going all the way up to university level. We wrote the teaching guides to go with them. We had some interactive parts as well. And I just want to show you a sort of musical collection of some of the experiments, including in the second half, how we did things a little bit differently as well. So you can see here we're showing some fundamental principles, if any of you are physicists, of circular motion, kinetic theory of gases, Newton's laws, conservation of momentum in collisions. Sorry, this is turning to a physics lesson, I'll try to avoid that. The behaviour of diatomic oscillators, but you'll also notice that we're filming in HD from X, Y and Z directions. And the reason we were doing that was for the next stage, because this sort of stuff has been done before, but not in HD. But what we did next was genuinely groundbreaking, because every single data set we analysed with tracker software, we video captured it, but we also put it into a platform so students could pick the variables that they wanted to analyse themselves. And that meant that your classic physics demonstrations could be used all the way up to first year university standard. That kit is still up on the ISS at the moment, and those resources are now in use around the world in schools and universities. Now, human spaceflight is probably the most visible aspect of space exploration, but there's far more to space science than just human activity. And what I've got coming up now, and sorry, I've got my dreaded technical issues again. Now, half of my visuals are missing here, so just excuse me for a second. I'm going to escape out of that. There we go. We are sort of behaving ourselves. I'm just going to cross my fingers. What I've got here is my representation of my answer to the question, what do you mean by space science? And to me, there's three parts, three simple parts to this. Firstly, it's looking out there, so astronomy. Secondly, it's going out there, exploration with robots and humans. But thirdly is the aspect that many people overlooked, which is the satellites that are not looking out there, but they're looking back here. This is the world of satellite applications that fundamentally underpin our 21st century way of life. And I want to go through a few examples. I think some of you in the galleries might have seen our meteorological satellites hanging somewhere over in that direction. Now, that wasn't a model. That was a flight spare for Meteosat 7, the satellite that took to these images and is still stationed 35,800 kilometers above the Indian Ocean. And the reason I wanted to show this is that, we take weather forecasting for granted now. But the information from meteorological satellites just in relation to hurricanes, cyclones, typhoons, which is three different names for the same phenomena, it saves hundreds of thousands of lives every year. Now, of course, as humans, we have evolved to see a narrow range of wavelengths. And so what I've got here is a representation of the colors of the spectrum that we can see, ranging from violet light with a short wavelength of about 420 nanometers, all the way up to 700 nanometers for red light. But of course, there's a whole range of wavelengths of electromagnetic radiation, of light effectively, that the human eye can't see. And if we can start using these in space science, we're getting more data, we're getting more understanding of the fundamental systems that we're looking at. And I want to share with you some examples. This is the United Kingdom in the summer of 2003, and we're seeing it in processed near-infrared. So these are wavelengths of light, slightly too long for the human eye to be able to detect. This is the United Kingdom in June, and this is the United Kingdom 4 months later. The difference is 95% of it due to trees losing their leaves and, of course, changes in agricultural use of land. Because we can use near-infrared and process it to measure the health and the distribution of plants. We can do this on national scales, we can do this on global scales, but we can go right down to individual fields. So what you're seeing here in this image of the Lashkargah in Helmand province is you are seeing opium production and poppies that have been growing and monitored. We can even go down to individual fields now with the levels of resolution that we have. I think many of you will have been following in the news the record pollution levels that we're seeing in Delhi and in Punjab and other cities in northern India. In this case, we've got nitrogen dioxide levels. Okay, we can monitor pollutants in the atmosphere right down to the resolution level of individual cities by looking at how the light is being, across many wavelengths, distorted and modified by the presence of these aerosols. This is nitrogen dioxide in the atmosphere, but we can also see the trend for carbon dioxide levels going up in the atmosphere. There have been all sorts of arguments about climate change, and many of those and many of the questions that are rightly put forward by climate change deniers are because the evidence set might be, one tree that was cut down in Siberia 300 years ago and one set of tree rings. But we've now got an armada of satellites monitoring the Earth effectively in real time, looking at the health state of the planet. In this particular set, you can see carbon dioxide levels in the northern hemisphere, and yes, they go up and down every season, because in the northern hemisphere, as the plants come into full blossom and the trees get their leaves, you have a slight reduction in CO2, but you can see how the trend is going upwards. And I think you would have seen on the news recently, we have exceeded, only for the second time ever, a global average figure of 400 parts per million of CO2 in the atmosphere. And what you are seeing here, again, forgive me for this, what you are seeing here is not working. I'm actually just going to escape from this and run it in the PowerPoint deck because it's a nice animation. What you're seeing here is the seasonal hole in the ozone layer that forms over Antarctica. This is from last year, and this is a legacy of the CFCs that we were using up to the 1980s in our deodorants, in our refrigerants, that were going up into the stratosphere, were ripping apart triatomic oxygen, that's ozone, Earth's natural sunscreen, and causing this annual hole to form over Antarctica. Now, this was only discovered, its existence was confirmed because of observations from space. Within 3 years, we put in place the Montreal Protocols to try to limit CFC production, but these CFCs, they stay in the stratosphere for more than 50 years. And so we have been affecting the environment. Space science is giving us one set of solutions, but it's amazing how long these effects can last for. The next animation I want to show you is possibly my best one. I'm going to chance it by trying to run it on full screen, but if it doesn't, I'll go back now. This is working fine. This is a combination of visual imagery and computer fluid dynamics modeling. We're going over a period 2 years ago of September going into early October. What they've done is they've superimposed images of the northwest hemisphere here with data related to smoke, sea salt, and dust coming off the Sahara. And the reason we're doing that is because when we are looking at rainfall, when we're looking at moisture in the atmosphere, we need what we call nucleation centers for the water vapor to condense around to create rainfall. And I always think this is like a visual lava lamp here. You can see the forest fires burning in North America. You can see the conveyor belt of hurricanes. But look at Hurricane Ophelia that developed far more east than we normally get. And of course, when we look at all the dust blowing off the Sahara, Ophelia took all this dust, and if you remember in the United Kingdom, the day that the skies went orange because of the Saharan dust, this was it. Now, we had this sort of visualization capability 15 years ago in satellites. What we didn't have was the computer fluid dynamics modeling capability to be able to integrate together to give a new data set and improve our understanding. And this final data set is taken from 3 British-built instruments that were orbiting the Earth over a period of 11 years, and we're looking at sea surface temperature, looking at the scale on the right-hand side. What I love about this particular data set is we see that, the UK is kept moderate in its climate by the effect of the Gulf Stream, so we don't get these savage winters and baking summers that you get in northern Canada that you'd expect from our latitude. As we move our viewpoint down towards Antarctica, this is absolutely astonishing. You see how the continent, the size of Australia, almost doubles in size every Antarctic winter during June and July because of this temporary sea ice shelf. We also see how little the waters of the Southern Ocean mix with the rest of the Earth's oceans. And changing our perspective to equatorial and tropical, you can see the powerhouse effect of ocean currents driven by temperature differences. The reason that we have hurricanes and typhoons and cyclones is because of sea surface temperatures above 27 degrees centigrade that are literally winding up those systems. We know now that not only is climate change real, but we're starting to get a better understanding of just how critical this issue is. And it's only been possible by having these platforms in space orbiting the Earth. But for me, the most pressing issue that we face, apart from climate change, and maybe even more important than climate change, it's the issue of global population. I was born in 1968, and then the Earth's population was 3.5 billion. Today, it's 7.5 billion, and the projections are by 2050 will be well in excess of 9 billion. We know that the challenges of feeding global populations or regional populations and access to water are major drivers when it comes down to national conflict. And what I'm showing here are the most critical factors when it comes down to food production. And you've got the obvious ones, like, for instance, the air temperature and the amount of rainfall, but what about the ratio of rainfall to evaporation? How moist is your soil? Where's the runoff water going? What are the wind speeds? These are critical quantities which can only be measured in real time from space. And so to really address these problems of the future, we need to have these systems orbiting the Earth. And of course, in our 21st century way of life, we take for granted the fact that we've got almost instantaneous sports coverage, news coverage from around the world. We now live in a world where events on one side of the planet will have geopolitical ramifications globally within hours. And that's only been possible because of this ring system of telecommunications satellites orbiting the Earth. It's no longer the case where I cannot transmit a radio signal from here to Paris because of line of sight. I just broadcast it up to a satellite, that relays it to the next one, and down to the ground. And of course, anybody who's got a mobile phone which has got some type of app which is using navigational capability is relying on satellite positionings and timing signals from a network of navigation satellites like the GPS network. Now, this is the revenue generation side of the space sector. I'm not here to give a sort of business studies lesson or overview, but what's interesting about these figures, about the global satellite revenue generation, is that those annual figures are not in millions of dollars a year, they are in billions of dollars a year. The figure for 2018 was $380 billion a year of direct revenue generation. Space activity pays for itself many, many times over. And I think the most surprising thing here in the United Kingdom is not only have we got a world-class space sector, not only is it growing, these are two government-commissioned studies showing the difference between 2016 and 2018. You can see the revenue generation, you can see the number of jobs in excess of 40,000. But the interesting thing to me is that when we look at this bottom figure here, more than 15% of our gross domestic product, our national wealth, is critically dependent upon these services from space. That's why space is part of our critical national infrastructure. Now, I had a representation here. I'm not going to risk coming out of this PowerPoint because this computer has obviously had a long day. But what you can do, if you just remember, and I'll give you the PowerPoint, if you remember this particular website, this is great because you just go there and you will get live, real-time visualization of all the satellites orbiting Earth. At the moment, there are about 2,200 active satellites orbiting the Earth. But things are changing, and they're changing quickly. Because most of these satellites are really big, you launch them into space, and they have to be up there for many years at a time. What if you can make much smaller satellites, cheaper to launch? What if you can network these satellites together with the right data handling capabilities so that we can have them orbiting much closer to the Earth? This is the world of satellite constellations, and we are building satellites as small as a Rubik's Cube. We call these CubeSats. And the idea is, and this process has started already, is that if you launch hundreds or thousands of these and network them together, you can have the communications capability that makes satellite internet a possibility without any latency at all. And so when you see images being put forward like this by Astos Solutions, the idea is have a global network of hundreds or even thousands of these small satellites. You have challenges of network communications, but they are manageable. And we're going to get a new era of satellite provision for internet capability in parts of the world where it's impossible to put in the ground architecture that you'd normally expect. And what is incredibly exhilarating but frightening about this is the numbers of satellites that we're going to see over the next 10 years. Because, SpaceX has already launched its first generation Starlink satellites. OneWeb are well on track now for 720 satellites in orbit. I think Samsung have abandoned their plans, but in the next 10 years, we could see not 2,000 satellites orbiting the Earth, but more than 25,000 of them. And, the challenges of making sure we don't get what we call conjunctions or collisions, they are not insignificant. We've got some real challenges when it comes down to the issues of space junk in the future. But I'm looking at my watch. I've got about another 6 or 7 minutes, so I just want to share with you some final perspectives. It's been a bit of a whistle-stop tour of the world of space science, but what about philosophically? What difference has it made, and what have we discovered about our own place in the universe? I first fell in love in astronomy when I was 5 years old. Now, I grew up in South London. You don't really see the night sky from South London, from Croydon, if anybody knows that area. But I was given a book on astronomy, and this was the best image we had at the time of the planet Saturn. And yes, it's a gas giant planet. We knew it was big. But back at that time, it was the only planet that we knew had rings. We knew that it had 9, possibly 10 moons, and that was pretty much it. And that's the best view we could get from Earth. If you'd have told me in my lifetime that we would rewrite our textbooks on all the planets of the solar system, I knew it was coming, but the magnitude of the change was absolutely unbelievable. This is a view of the planet Saturn that we can never get from Earth. It's a view taken by the Cassini spacecraft. This is a spacecraft that went on a 7-year, billion-kilometer odyssey to the planet Saturn and then went into orbit. It wasn't just a NASA mission, it was European Space Agency. And why this image is impossible to get from Earth is this is Saturn eclipsing the sun. The sun is being obscured by this giant planet, so we're seeing incredible levels of detail within the ring system here. Not only is this an image that is incredibly beautiful, it's incredibly data rich. But again, at an emotional level, what I really like about this image and why it's impossible to get from Earth is what we see here. Because these 2 dots are moons of Saturn, but this dot isn't. In fact, when we look at this dot here, and we look in close, it's a double dot. This is the Earth, and this is the moon. Every single one of you is in this image. You are on that tiny collection of pixels there. Earth is indeed a pale blue dot, as Carl Sagan so famously said. But we've also seen images like this. This is not computer enhanced. This is 30. Bear with me. Bear with. Let's try one more time. Otherwise, I'll run it in that minimal mode. This is 30,000 images taken by the Cassini spacecraft and not enhanced on one of its orbital passes of Saturn. It did hundreds of these. We have just swept past the ice moon of Mimas, a moon that when it was imaged like this looked very much like the Death Star. We're flying now past the plane of Saturn's rings. Never forget that this image would cover your entire field of view. The rings have got a width of 170,000 miles. That's what, 300,000 kilometers nearly, but a thickness of about 5 kilometers. We're seeing incredible details in these rings, and we're about to do a pass over the ice moon of Enceladus, which until 2005, and until these images, was probably amongst the most boring places in the solar system. So whenever we look at these images from robotic explorers, they're not just beautiful. They don't just have grandeur. They are incredibly science-rich. And here we go, sweeping past Enceladus, and the camera looking backwards. Of course, this was a completely automatic procedure because the spacecraft was so far away, it would take radio signals more than an hour to get there. So there is no way of directly controlling those systems. You have to pre-program. So in my lifetime, we have seen these worlds, the moons of the gas giant planets, transformed from points of light in the most powerful telescope to worlds of fire. This is Io, one of Jupiter's moons, that's the most volcanic object in the solar system. We've seen worlds of ice. Now, this is Enceladus in scale against the United Kingdom, and this is what we knew about it before 2005. But in 2005, when Cassini flew by, we saw something astonishing. We saw salt water erupting from the interior of Enceladus through cracks in the ice. We had confirmation that underneath this ice, we've got an ocean of liquid water. We infrared mapped those cracks. They are warm. Not only that, when we flew through the plumes, we discovered organic molecules, the building blocks of life. So suddenly, Enceladus has gone from being the most boring place in the solar system to one of the most likely targets to look for life elsewhere. And this has happened not just in my lifetime, this has happened within the space of the last 12 or 13 years. And of course, you know, the Hubble Space Telescope, not the biggest space telescope, but the most famous instrument ever built. And I just want to share some of my almost favorite Hubble images. You know, Hubble's rewritten so many of our ideas in astronomy since it was launched in 1990 and since it became operational in 1993. You know, we've seen wonderful images like this. This is M16, the Eagle Nebula. This is a region of space. A nebula is like a cloud of material in which new stars are forming. To give you an idea of scale, our entire solar system would fit into that red dot that I'm just projecting on the screen. But what we're in effect seeing is the early history of our solar system. Because 5 billion years ago, our solar system formed out of a cloud of dust and gas just like this. Hubble has shown us the birth of stars. We've also seen the death of stars. This is NGC 6543, or the Cat's Eye Nebula, as I prefer. And this is what happens at the end of its life when a star like our Sun, in 5 billion years, runs out of fuel for nuclear fusion and puffs off its outer layers to form a planetary nebula. And there's a close-up showing shockwaves moving through the material that it's thrown out. We've also seen wonderful images like this. You know, this is M51, the Whirlpool Galaxy. You can see it from the ground with a telescope, but not in this sort of detail. Now, this isn't a collection just of hundreds of stars or thousands of stars like our Sun. This is a collection of 100,000 million stars like our Sun. It's so far away, the light has taken 29 million years to get here, and Hubble has imaged thousands of galaxies in unprecedented levels of detail. But what I want to do now is show you what I think is the most transformational image that's ever been taken in astronomy. But before I do this, I just want you to indulge me here. I want you to imagine that on your thumbnail, you are drawing a 1 millimeter by 1 millimeter square. Now, this is good, because it's the end of the day, and some of you are looking at your thumbnails, and you are pretending to do this. And what I'd like you to do, for the maths, we need to do this, is to now extend your thumbs out like this. For the maths to work, this should be 1 meter from your eyes, so really stretch it out. Okay, look upwards. Now look at the size of that imaginary square on your thumbnail, and now put your hands down, because I know some of you are getting a little bit embarrassed, and you're thinking, why is he doing this? Well, what the Hubble Space Telescope did is it looked at an empty patch of sky in the southern constellation of Fornax, and the angular size of this patch of sky was 1/20th of a degree, which is the same size as your 1 millimeter by 1 millimeter square when it's held over here at this distance. And Hubble looked at this patch of sky and began collecting photons. And on its next orbit, it looked again. And its next orbit, it looked again. And it did this over 840 orbits of the Earth with an exposure time, for any photographers here, approaching 1 million seconds. And as it collected more and more photons, we saw that this wasn't an empty, tiny scrap of sky. What emerged was this image that I think is the most incredible image ever taken in astronomy. And this is it. Now, you're all being really polite, but I can see some of you are thinking, hold on a second, look at the grandeur, the drama, the beauty of these. You know, not that one, that one. Why is he getting so excited and so worked up about this? Well, it's the context, because what emerged in this image, when you look at the HUDF, is 10,000 dots. But when we look closely, each of these dots is not a star. Each of these dots is a galaxy. And so I don't know what's more amazing. The fact that in a tiny scrap of empty sky, Hubble saw 10,000 galaxies, each with 100,000 million stars like our sun. Or the fact that we can use that image and GCSE mathematics, high school mathematics, to make an approximation of the number of stars in the universe. Now, I promise you I wasn't going to give you a physics lesson, but a tiny bit of a maths lesson. If anybody's interested in what you do, what you're effectively doing is you construct an imaginary sphere surrounding you of 1 meter radius, calculate its surface area in millimeters squared, multiply by 10,000, multiply by 100 million. Okay, I'll stop there. What's the number that we get? This is an approximation that school students can work out of the number of stars in the universe. And if you are doing high school physics, you can also show, that's probably an underestimate, almost certainly, you can also prove that there are indeed more stars in the universe than grains of sand on all the beaches of planet Earth. That's what Hubble has shown us. Now, in conclusion, because I'm down to my last 2 minutes, we're at an incredible junction now in space science in terms of looking for the future. Right now, the European Space Agency is having a meeting in Seville where we're deciding our future priorities and what we're going to do. I've been involved in this process as a science advisor to the Human and Exploration Directorate, and I want to finish with just a short 2-minute film and just a couple of slides. This is what we want to achieve in the future. Currently, we are on board the International Space Station. In Europe, we have 7 active astronauts. 6 of them have already flown on the ISS. That's Luca Parmitano on his first mission. He's currently on the ISS now. And you just get a taste of life, the experiments that we're doing, and what we are planning for in the future. Now, this is in low Earth orbit. We're only 250 miles, 400 kilometers above the Earth. But we're planning for a radical change, because after a hiatus of nearly half a century, we now have a roadmap to return humans to deep space again. We have developed the Orion spacecraft, a collaboration between NASA and the European Space Agency for returning humans to the moon within the next 6 or 7 years. Tomorrow, almost certainly, we're going to have a public announcement about our next selection for our next European astronauts. We've got a continuation of our robotic exploration, not only of the moon, but also of the planet Mars. We've sent spacecraft before. Next year, we're sending Europe's next robotic mission to Mars, the ExoMars rover, which is built here in the United Kingdom. But ultimately, our plans are to get humans onto the surface of Mars by the 2030s. And the reason we want humans is we can have the most sophisticated robotic systems, but nothing has the flexibility and the response time and the agility of having a human scientist or field observer on an alien world looking for signs of life. So the ExoMars rover, as I say, going to be launched next year. We've got NASA's Mars 2020 mission going, and also a Chinese mission, and this is the Orion spacecraft. Now, we've had long-standing plans to build what we call the Gateway Station, a small station orbiting the moon. And then earlier this year, President Trump changed the stakes. This was the announcement of Project Artemis. Artemis is the twin sister of Apollo, and President Trump set this as the top United States priority, Space Directive 1, to return humans to the moon in 5 years and have the first American woman, the first human, or the first woman, of any country to walk on the surface of the moon. This is technically achievable, and the odds are changing. Europe is involved. I think the odds are now 70% that I will see humans on the moon once again in my lifetime. We've got the mission architecture in place. We've got the target region at the moon's south pole. And we've got the launch challenges well scoped out. Congress still needs to release the money. But why this is so important is that the last humans to walk on the moon was nearly half a century ago. I remember this. It's one of my earliest memories in 1972. But back then, we had this astonishing photography that you see here. But the images that we captured with our video cameras were incredibly primitive. You know, this was the highest resolution we have. And this didn't give us any experience, really, or any connection with what the astronauts saw with their own eyes. When we go back to the moon with human explorers in 5 years or less, they'll be taking HD cameras with them. And we'll see for the first time Earth from the moon as the original Apollo astronauts did nearly 50 years ago. This is an image taken from Lunar Reconnaissance Orbiter. This is taken in HD with the resolution of the human eye for somebody orbiting the moon. But what's most astonishing about this image, and it was experienced by the Apollo astronauts, is what we see, because this is a world unique in the solar system. It is a world teeming with life. Life, unlike any other planet in the solar system, life has fundamentally altered the atmosphere, the geology, the oceans of planet Earth for billions of years. And this is detectable across astronomical distances. If I was an alien visitor to our solar system, I'd ignore every other planet and I'd come hot-footing it to Earth. This is a very special place, and I would argue that our most significant discoveries on space science have been about how special our home planet is. And I'd like to leave you with the words of the commander of the Apollo 15 mission, Dave Scott, when he first set foot on the plain in the valley of Hadley-Apennine in July 1971. While standing here today, I'm reminded of a fundamental truth. Humanity must explore, and this is exploration at its greatest. Now, for a long time, I thought he was talking about space exploration, but I now believe he was talking about the voyage of exploration that humanity has only been able to undergo because we have successfully harnessed science and technology. And if we are to continue that trajectory of progress, it is vital that we support the next generation of scientists, of engineers, and of explorers. The benefits that will accrue will benefit all of humanity, and that is why at the National Space Centre our fundamental goal is to educate and inform and inspire people about space. Ladies and gentlemen, thank you very much.